The next big topic we need to look at is Carnot efficiency and the Carnot cycle. Sadi Carnot was a French scientist. His father actually was a revolutionary general. If you ever study the French Revolution in any detail, you'll encounter Laszlo Carnot's name. He was also one of the Directory for a while. Just a historical side note. The Carnot cycle is very important. I'll get to why in just a second, but here's how it works. It's a theoretical cycle. In reality, you never really make one that's perfect, and worse, no one ever makes one really at all. And I'll get to why that in a second too. But the idea is this. You start with an isothermal expansion. So you take your cylinder of gas with a piston, and you put it in contact with a hot reservoir. The cylinder is already at the hot temperature, so it isothermally expands. It never gets hotter. Technically, of course, you're never exactly isothermally expanding. In order to take in heat from the hot reservoir, you have to be a little bit cooler than the hot reservoir at minimum, which is one of the reasons you never get a perfect Carnot cycle. But you expand it for a while. This is the work phase, by the way, when the piston's expanding and pushing on something, doing work for us. Once it gets to a certain point, you stop, you pull it away from the heat, wrap it up in super insulation, so no heat can flow in or out, and you do an adiabatic expansion. Okay? During this expansion phase, since there's no change, no heat flow, and work is being done because it's still expanding, the internal energy must be going down. That's where the energy has to come from. Internal energy going down means cooling, so we've actually dropped down to a colder temperature. Now we're at the cold reservoir, and so we isothermally compress, okay, the gas. This is where it contracts on its own because it's cooling. Down, 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 down. Okay? Until we're at just the right spot in the compression. We wrap it up in insulation again. We let it finish contracting while heating, or we push on it. That puts internal energy into the system. Okay, this should be an adiabat as well. Okay, until I bring it back up to the original point, thus completing the cycle. The work, of course, is the area inside of here. So what's so cool about a Carnot cycle? Well, they're not very cool in the fact that they're very, very slow. A real Carnot engine, if you did build one, modulo even the imperfections you're going to have, is never going to be very quick. And I remember a statistic I read once that if you built one, to get your car up to 35 miles an hour would take something like 2 weeks. It's, absurdly slow working. But what makes the Carnot engine so amazing is that the efficiency of a perfect Carnot engine is always greater than or equal to the real efficiency of any other engine. Carnot proved that this is the best engine you could possibly imagine ever building. I mean, again, it's a theoretical engine. It's not one you could actually build anyway, but even if you got perfectly close as you could get, it would be the most efficient engine possible. And here's the cool thing. He also showed how much work you get out for how much heat flows in through here. And what he showed was the Carnot efficiency goes like temperature hot over temperature cold over temperature hot. Okay? Or if you prefer, 1 minus T cold over T hot. This isn't the definition of efficiency. It should really be about Q over, work over Q, but this is what it turned out to be. So for example, we can do a case where T cold, let's say an engine's being cooled with something like liquid nitrogen, which I believe is around 120 kelvins, and say the hot area, the part that's burning, is at an amazingly hot 1000 kelvins, okay? These are both really unrealistic. In that case, the Carnot efficiency is 1 minus T cold over T hot equals 1 minus 0.12, which, check my math, should be 0.88 efficiency, or 88%. That is greater than or equal to the real efficiency of any engine. Okay? So, for example, so first of all, 88% is actually not that efficient in some sense. It's really good overall compared to most engines, which are like at best 20, 30, 40% efficient, but still, it's kind of depressing. I could tell you, though, that, okay, the real engine that somebody built working at these temperatures was 90% of the Carnot efficiency. In that case, the efficiency would be 0.9 a Carnot, which would be around zero point 0.8 efficiency, if I'm doing the math right in my head here. So this is the Carnot efficiency. It is the ideal efficiency. It is the limit to which you could possibly take an engine. And you'll notice pretty quickly as you do some calculations that for realistic temperatures, it is still surprisingly low. And then on top of that, you got to remember that real engines never work like a Carnot engine, and therefore it's even worse than that, okay? The second law of thermodynamics says that, in fact, no engine can ever be 100% efficient unless one of the ends operates at absolute zero, which we'll later find out you also can't do. So you'll never get a 100% efficient engine, and you can kind of see why from the Carnot efficiency right off the bat. Okay, this is always going to be less than 1, pretty much, because this term is always non-zero, pretty much. Okay, I will see everybody Tuesday.